Hey everybody, it's Mr. Doro. Today we're going to learn about balancing chemical equations in order to fulfill the law of conservation of mass. You can check out the objective, what you should know when you get done. We need to start out with the law of conservation of mass. The law of conservation of mass is that mass cannot be created nor destroyed, and that the total mass before the reaction, which is the reactants, is equal to the total mass after the reaction, which is the product. So you'd add all those masses together and you would find out that your mass before equals the mass afterwards. In our little picture that we have down here on the bottom, this is an incomplete combustion reaction. If it were a complete combustion reaction, then your only products would be carbon dioxide and water, but this one has also ashes that are in there. And so wood is a hydrocarbon, reacts with oxygen. If you take the total mass before the whole thing and add it or compare that to the total mass after, the carbon dioxide, the water vapor, and the ashes, then you're going to find out that the mass before equals the mass afterwards. When balancing an equation, you have to know the difference between a coefficient and a subscript. This picture shows coefficients in red. They're big numbers that are written before an atom or a molecule. The subscripts are shown in blue right here, and they are small numbers that represent how many atoms are in each molecule. Now, we're going to use subscripts when we have to write the skeleton equation, and once we have the skeleton equation written, then we use coefficients to balance out the equations. So it's very important that you know that coefficients are used to balance the equations each time. Now, a coefficient goes with everything that comes after it, and you would multiply these with a subscript. So for example, right in this area right here, 2 sets of H2s would represent 4 H's. This would be an understood 1 since there is no coefficient. That's 1 O2. And this would be 2 sets of H2O, so 4 H's and 2 O's. Here are some basic rules for balancing equations that you'll want to write down. You have to have the same number of each type of atom on each side of the arrow, and you have to have, if you have a carbon on the reactant side, you have to have a carbon on the product side also. You have to have the same type and the same number of each. So here's how you do that. Sometimes when you write the equation, the skeleton equation, it does not have the same number of each atom on each side. So there's a way that usually works best, and here's the way I usually tell you to do it that works best. Look for a polyatomic ion. If there's the same polyatomic ion on each side of the arrow, then group them together and balance them first. I'll show you what that means in a minute. You should be writing this down though. Balance the metals next, then the nonmetals. Save hydrogen for last, and then oxygen for the very last. Usually that'll work out the best. There's no guaranteed method on this, but usually that ends up being the best. This is a decomposition reaction of silver oxide into silver and oxygen. And it is a skeleton equation, so it's not balanced, so we're going to go ahead and balance it. When we're starting out, the easiest way to do this is to, right underneath the arrow, list each of the elements. Since there are no polyatomic ions in here, I'm just going to list the silver and the oxygen. And I'm going to go ahead and list how many are on each side. Over on this side over here, we have 2 silvers, and so I'm going to put 2 for the silvers here, and we have 1 silver over on this side. The oxygens on this side, we have 1 oxygen and 2 oxygens because of the subscripts over here on this side. This one has no subscript. So we can see that the silvers are off and the oxygens are off. So our rule is that we need to take care of the metals first, so I'm going to take care of that silver. And in order to make this silver, 2 silvers on this side, I don't put a 1 in front of this. Instead, I'm going to put a 2 right there. Now that means 2 silver atoms. That changed this to 2 silver atoms. And so my silvers are good now. Then I need to take care of the oxygens. Now I have 2 oxygens over here on this side, right here. Only 1 here, so I need to put a 2, but I cannot put the 2 right in between here. You cannot put coefficients in between. So we need to make sure we put coefficients at the beginning of a molecule. So I'm going to put a 2 at the beginning of this molecule. That makes 2 oxygens now on this side, but that 2 at the beginning also changed the silvers. Now I have 2 times this 2 for the silvers, and so that makes me have 4 silvers. So I got to fix that now too. And in order to fix that, I go back over here to this side, and I will just cross this out because it won't let me erase right now. But I cross this out, and I need 4 total silver, so I'm just going to make that 4 now, and that makes everything all nice and balanced. And you can see from this picture right here that as we started out, we had Ag2O. These are the 2 silvers and the 1 oxygen. And on the product side, we only had 1 silver, and we had O2, or 2 oxygen atoms, right here. So that was unbalanced. But then when we balanced it now, we have 2 sets of Ag2O, which makes 4 total silvers and 2 oxygens. And over here now, we have 4 Ags and O2, which ends up being balanced with the same number of each type of element on each side. This is a double replacement reaction, and you can see it also has polyatomic ions, and so what we're going to do is we are going to balance this according to the law of conservation of mass. Now, instead of breaking this down to Al, S, O, H, and Ca, I'm going to keep together the SO4, because I have an SO4 on this side and an SO4 on this side, and I'm going to keep together the OHs. It just goes a whole lot easier because I have one on each side. And so what I'm going to do is I am going to write underneath here what I have: Al, Ca, SO4, and OH. And I'm going to say how many of each one I have on each side. Al's on this side over here, I have 2 because of the 2 subscript right here. And on this side, I only have 1. This 3 only goes with the OH. So I'm going to put 1 over here. Calcium's on this side, on the reactant side, I have 1. And on the product side, I have 1. SO4's on this side, I have 3 sets of SO4. On this side, you're going to think that we have 4 SO4's, but we don't. We only have 1 set of SO4's. And on this side, the OHs, we have 2 sets of OHs. Over here, we have 3. So I'm going to write those in right now. 3 sets of SO4 here, only 1 over here. OH, I have 2, and I have 3 over here. Now again, we're going to go through our steps. We start with the polyatomic ions. I have 3 SO4s on this side. I need 2 more over here, but I don't put a 2 in front of it. I put instead a 3 because now I have 3 sets of SO4. That changed my SO4s, but it also changed my calciums. Okay, so now my SO4s are good. My OHs, my hydroxides, I have 3 on this side and 2 on this side. Now we cannot put a fraction or a decimal or anything like that as a coefficient. So what we need to do is we need to find the I think it's called the least common multiple or something they both go into, the lowest number that they both go into. And so the lowest number they both go, 2 and 3 both go into, is going to be 6. So I need to put something in front of the CaOH2 to make it 6 hydroxides, and that would be a 3. I cross this out. That makes 6 here, but I also changed my calciums to 3. And then I'm going to put a 2 right here because I want 6 hydroxides. That makes 6 here, but it also changes my aluminums to 2. And magically, that all worked out. It doesn't always work that way, but on the first try, those all worked out just fine. And now we have our balanced chemical equation. I always go back and I recheck it though. It's very quick to recheck it. 2 aluminums here and 2 aluminums there. The coefficient in front of the aluminum means 2 aluminums. This one by the subscript means 2 aluminums. I have 3 SO4s here, and the coefficient here means 3 SO4s right there. I have 3 calciums due to the coefficient, 3 calciums due to the coefficient here, and 3 times 2 hydroxides, that's 6 hydroxides, and 2 times 3 hydroxides, that's 6 there, so now we're all balanced. Here are a couple of balanced equations and pictures that go along with them. If you look at this balanced equation that we have right here, CH4, that's methane, reacts with 2 O2s to produce CO2 and 2 H2Os. And if you look at the pictures right up here, since there's nothing in front of the CH4, it means that there's only 1 molecule of methane. Reacts with the coefficient right here means 2 molecules of O2 to produce 1 molecule of CO2 and 2 molecules of water. And you see that we have that picture here. This is another combustion reaction. This is propane. And here's what propane, pictorial definition of propane. And so you can see we only have 1 molecule of propane. They're all joined together, so that makes it 1 molecule. These are not joined together. We have 5 separate molecules of oxygen. So 1 molecule of propane reacts with 5 molecules of oxygen to make 3 separate molecules of CO2 and 4 separate molecules of H2O. Some combustion reactions can be pretty tough. That's why I set this one up for you. I got everything all counted up for you except for the oxygens on the product side. In the carbon dioxide, we have 2 oxygens here, and we have 1 oxygen in the water. So that gives us a total of 3 oxygens on this side. So what we're going to do is follow our rules. There are no polyatomic ions and no metals. So we're going to take care of the carbons here first, the non-metal. And so we have 4 carbons in the reactants and 1 in the product. So I'm going to put a 4 in front of the CO2. That changes my carbons to 4 now. And my oxygens, it changes to 4 times this 2 right here. That means 8 plus this 1 more. That gives me 9 total oxygens. I'll take care of the hydrogens next, and then I'll take care of the oxygens last. So the hydrogens, I have 10 total on this side, and I have 2 on this side. I need to make 10, so in order to make 10, I'm going to put a 5 in front of this, because now I do the 5 times the 2 gives me a 10 total, and so that takes care of my hydrogens. And that also changed my oxygens, so I have 4 times 2, that's my 8 oxygens, plus another 5, so that gives me 13 total oxygens. Now you see that I got a tough time because I can't put a fraction or a decimal or anything like that as a coefficient. I have an O2, so nothing that I can multiply by 2 would give me 13. When you have an odd number on one side and you have something like an O2 on the other side, there's a special trick you can do, and it is doubling all of the coefficients. So this coefficient in front of the C4H10 was an understood 1. I'm going to make that a 2. I'm going to come back to this oxygen here in just a second. This one right here is a 4, so I'm going to change that and make it, now normally what I'd like you to do is erase it, but I can't erase on this function right here. So I'm going to make that an 8, and this 5 over here, I'm going to make a 10. Now that changed some things. So that changed my carbons on this side to 8, and it changed my carbons on this side to 8 also. It changed my hydrogens to 2 times this 10 right here, which is 20 on this side, and my hydrogens on the product side to 10 times 2, which is also 20. And then my oxygens, I'm going to count up my oxygens on this side over here. I got 8 times 2, which gives me 16, plus another 10 times this one right here. So 16 plus that 10 gives me 26 oxygens over here. Now I have an even number. I can put a 13 in front of this one to give me 26 oxygens here. This is an acid-base reaction, and you can tell it's an acid-base because it has an acid, something that starts with an H, and it has a base which has a hydroxide group. Always going to make a salt and water. The salt is just any ionic compound. And the water, the best way to think about this to balance these is if you think of it as HOH. It's still H2O, but we're separating out the hydroxide group and a hydrogen. So now we can count them separately. If we look at all the rest of these here, the SO4s, we have 1 set of SO4 on each side, so we don't have to do anything with that. We have 1 calcium on each side, but the OHs, we have 2 OHs over here, and we only have really 1 set of OHs over here. So if we put a 2 in front of this, then that means that we have 2 sets of OH, which cancels this one out, and we have 2 H's all by themselves, which can cancel these ones out also. And then it ends up being balanced. Balancing can be very frustrating, but if you keep at it, you're going to do just fine. Don't get too frustrated. If you get upset, step away from it and come back to it later. Okay, now it's time for you to try it. I want you to write these out on your notes, and underneath each arrow I'd like you to write the elements or the ions and then say the number of each and balance them. Good luck. Go ahead and pause it now.